Okay, week 11 Physics CA for 9S. Yes, I bought a new mic. An object is moving along a straight line. Its motion is described by the following equation. So, if you remember, we took this a few weeks ago, and the equation is xt equals the initial position plus vt. So we're just comparing these two equations. We can see that the initial position is 2.2 and that the velocity is negative 0.8. So you can see here the velocity is negative 0.8 and the initial position is 2.2. A runner moves uniformly along the x-axis at a speed of 1.1 meters per second in the direction of the positive sense of the x-axis. Initially, the runner is at initial position negative 2. So we can use the same formula as last time, like we were just using the last question. So we need to find the position, and our initial position is negative 2 plus velocity, which is 1, times the time, which we have here is 5. So you end up getting 3. And then for the second one, we just clear that. Again, use the same formula, but now since we have this one, which is 3, we can do 3 equals the initial position, which is negative 2, plus velocity, which is 1, times t, which we need to find. So this is obviously just going to be t. So you take this to the other side, and it's going to be 5. Okay. A jet plane initially at rest starts moving with the constant acceleration of 4 meters per second. Which equation best represents the displacement of the plane? So look at the options here. We can see we have time in the options. So that's why we're going to use our formula accordingly. So let's just write down our given. We have the initial velocity, which is 0, and we have the acceleration, which is 4, and they want the displacement. So in the equation we have time, in the answer key we have time. So let's just write down time. And then, but out of all of these, what they don't give us, what they don't want is velocity final, which is why we're going to use the equation delta x equals half of acceleration times squared plus the initial velocity times time. So right off the bat, we can see that the initial velocity is 0. So anything times 0 is going to be 0. So we can just cross this out. And now to get the displacement, we do half of 4t squared. So you get x equals t to 2t squared. An equation that is used when the motion is uniformly accelerated from rest. So writing down the equation, which they literally have over here, it's half of at squared plus vrt. So if it's at rest, that means the initial velocity is 0, so we can cross this out, and this is going to be this. A race car accelerates uniformly from 30 meters per second to 50 meters per second in 2 seconds. Okay, so let's write down what they've given us. They've given us the initial velocity, which is 30, the final velocity, which is 50, the time, which is 2 seconds, and they want us to find the displacement. And out of all of this, we don't have acceleration and they don't want acceleration. So that's why we're going to use this formula. So over v final plus v initial over 2 times time. So after replacing 50 plus 30 over 2 times 2, you get 80. A sport car needs a straight length of track of blank meters to accelerate uniformly at 5 meters per second from 11 meters per second to 41 meters per second. So let's write down our given. We have acceleration, which is 5. We have the initial velocity, which is 11, and we have the final velocity, which is 41, and they want the displacement. Now, out of all of this, we do not have time, and they don't want time. So, which is why we're going to use this formula. Velocity final squared equals velocity initial squared plus 2a times delta x. So, replacing 41 squared equals 11 squared plus 2 times 5 delta. Sorry, wait. Delta x. Okay, sorry, I accidentally said time, it was acceleration. So, you take the 11 squared to the other side. So, you get 41 squared minus 11 squared. So, you get 1560 and divide that by 10. So, you're gonna get your answer, which is 156. A racing car accelerates uniformly from rest and crosses the finish line in 12.32 seconds. The length of the trail is 402 meters and the car's acceleration to one decimal place is blank. So we have our initial velocity, which is 0. We have our time, which is 12.32. And we have our thingy, the delta x, which is 402. And they want the acceleration. I don't have velocity final, they don't want velocity final. So we're going to use this equation equals half of at squared plus velocity time. Now again, velocity initial is 0, so we can just cross this out. So we get 402 equals half of a times 12.32 squared. So 12.32 squared, and you're going to multiply that by 1 over 2, and then whatever you're going to get, you're going to divide that by 402, but make sure it's 402 divided by whatever you get here, and not this divided by 402. Like 402 has to be first. So you should get 5.3 after rounding. A car is moving along a rectilinear track with a constant speed of 15 meters per second. The driver suddenly notices a speed bump 20 meters ahead. The driver applies a brake, thus making the car decelerate at a constant rate of 6 meters per second squared. The car stops in 2.5 seconds. Okay, let's write down our given. So we have the initial speed, which is 15. Our acceleration, or in this case deceleration, which is -6. Our time, which is 2.5. And there's a speed bump 20 meters ahead. So first we need to calculate the stopping distance. So we're going to use the formula delta x equals half of at squared plus vit. So we're going to substitute. So you get delta x equals half of -6 times time squared, so 2.5 squared plus 10 times 2.5. So after calculation, you should get, so this, you should get negative 18.5, 18.75, sorry. So now we need to calculate how far away the thing is from the speed bump. So we need to calculate the distance between here and here. So you're gonna do 20 minus 18.75, and you get 1.25. Let's try that. So you get 1.25, and to the nearest option we have is 2 meters. So 2 meters away. A train moving along a straight track accelerates from 2 meters per second for 20 seconds. It then moves at a constant speed for 2 minutes and finally deaccelerates uniformly to a stop at 10 seconds. The net displacement of the train is blank. Okay, so we had this question last week and it was really hard, so let me explain it because last week I did not explain it that well. So a train accelerates from 2 meters per second for 20 seconds. This is the first part which we're going to solve because this has 3 main steps. So the formula we're going to use for this part, and specifically because you're not asking anything to do with delta x, we need to find the acceleration of this part, because here. So velocity final, which is what we don't have. So I'm going to call that velocity final equals the initial velocity 0 plus 2 times 20. So we get 40, which is our velocity final. Then we need to calculate the distance while accelerating. So we're just going to leave that on the side because we're going to end up using it later, yeah? So now we need to calculate the distance while accelerating. So you're going to use the famous formula, delta x equals half of at squared plus vit. And after replacing, you're going to get half of 2 times 20 squared plus 0, which is 400. So our first thing is 400. And now we need to find the constant speed. So we're going to use the URM formula, which is xt equals the initial position plus velocity times time. So now that we found the velocity final, which is what we need for this equation, which is 40, we can now, after replacing, we can do 40 times, and the second part of this equation is 2 minutes. So now we're going to use the time for 2 minutes, which is 120 seconds times 120. So that's basically how you get the seconds displacement, which is 4,800. And now to get the last step after all of this, basically, is to get the final displacement. You're going to do just a simple formula, VF displacement equals VF over V plus VI over 2 times time. So 40 plus 0 over 2 times 10. So you get 200 for the last one. And when you add, okay, leave this value when you're adding these because this is what you got in order to find these last two ones. So 4,800 plus 200 plus 400 is 5,400, which is this. The velocity time graph below shows a car starting from rest and accelerating for 5 seconds at the rate of 4 meters per second squared. Then the car moves at a constant speed for 4 seconds. At which interval does the formula x equals half of at squared applied? Okay, this also came last week. So as you can see here, at x equals at squared, let's see, where is this graph accelerating? It's accelerating from here to here, and that's between 0 and 5. And since this formula has acceleration in it, it's going to be from 0 to 5. At which interval does the formula x equal vt apply? So x equals vt. Now x equals vt is for URM. So it's obviously going to be at a constant velocity. and it's only at a constant velocity here, which is why it's going to be between 5 and 9. So there we go. The total distance covered by the car during the 9-second interval is blank meters. So this one is the 9-second interval, the whole thing. And we can split this into two shapes because we need to find the area of the shape in order to like find the net displacement. So we can split this into a rectangle and the triangle. So let's first find the area of a triangle. So it's base times height over 2. The base is 5, the height is 20, and you put that over 2, so you get 50. And the rectangle is just length times width, so 4 times 20, and you get 80. 80 plus 50 is 130 meters, which is the answer for part I. The velocity of the car at time 3 seconds is 12. For this question, you just have to follow the graph and read the graph. And the highest velocity of the car is blank kilometers per hour. So when you're transferring from meters per second into kilometers per hour, you multiply by 3.6, and when you're doing vice versa, you divide by 3.6. So it's going to be 72. Now for question. A particle initially at a point with coordinate x equals -2 is moving away from the origin at a constant speed of 5 in 10 seconds. The position of the particle will be. Now for this one, we're using the formula for URM again. So we have, so the formula is x equals initial position plus velocity time. So our initial position is -2 plus, now it's moving away from the origin, so it's going to be -5 for the velocity times 10, so you get -52. A man is standing on a rooftop of a building of height 85 meters. He tosses the ball vertically upward with an initial velocity of 15 meters per second. Take g as 10 meters per second squared. Okay, so we have the height of the building, which is 85, and we have the initial velocity, which is 15, and we have g, I guess, which is 10. And the formula we're going to use for this, also by the way, the final velocity for this is because when he's tossing it, like he's tossing it vertically, so the final velocity is going to be 0. So now the formula we're going to use, I'm going to write it over here. Velocity final squared equals initial velocity squared plus 2a delta x. Now, of course, like we can just cancel this out, 0. But now we need to take this one to the other side. So now we get 225. When we can just write it like as over 2 times now g, we're gonna take g again as 10 equals h, because we need to get this alone. Like when I say h, I mean this like as a variable, yeah. So you get this, you get 225 over 20, which is 11 points. So you get this, you get 11.25, and rounded to the nearest decimal, it's 11.3. And then for part B, the ball then falls down to the ground below. How much time does it spend in the air? Okay. Okay guys, to be honest, I don't know this one and I don't know this one, because I do not recall anything like that. So, because I tried applying the formula. The stopwatch is turned on as a toy car passes the x equals 3 meters mark on a track. The toy car is moving in the negative direction at a constant speed of 0.40. The position of the toy car at 2 seconds is... So we have a position which is 3. We have our velocity, which is negative 0.4 because it's going in the negative direction, and our time, which is 2. This is the initial velocity. So, the initial position. So that means you can use a formula for URM, which is initial position plus velocity times time. So 3 plus negative 0.4 times 2. So after putting that into your calculator, you should get 2.2. A toy car is initially moving at 2.50 meters per second in the positive direction. It starts decelerating at the rate of 0.20 meters per second squared. The velocity of the toy car 2 seconds later is blank meters per second. So the initial velocity is 2.50. The deceleration is 0.20, so it's going to be negative 0.20. And the time is 2, and they want us to find the final velocity. So by that logic, the formula we're going to use is, which means you can use the formula with no displacement. So velocity final equals initial velocity plus acceleration times time. So I'm going to call the final velocity h. So h equals 2.5 plus negative 0.20 times 2, and you should get 2.1 meters per second as your answer. The cyclist passes the start line with a speed of 2.80 meters per second in the positive direction while accelerating at a constant rate of 0.2 meters per second squared. The displacement of the cyclist in 20 seconds is blank. Okay, so what do we have? We have our initial velocity, which is 2.8. We have our acceleration, which is 0.2, and we have our time, which is 20, and we need to find our displacement. So we don't have velocity finite, so we're going to use the formula. I'm going to use a different color because it's going to be easier to see. Delta x equals half of acceleration times squared plus the initial velocity times time. So after just replacing, you're gonna get this 0.2 times 20 squared plus the initial velocity, so 2.8 times 20, so you should get 96. A particle at the origin starts from rest and accelerates at 2 meters per second squared. The particle will be 81 meters away from the origin in blank seconds. Okay, so let's write down what we do. We have the initial velocity, which is 0, and we have the acceleration, which is 2, and we have our delta x, which is 81. So which formula can we use? We can find time, but we don't have velocity final. Again, this formula, half of at squared plus vit. So after replacing, you get 81 equals half of 2 times squared. So obviously the initial velocity is 0, so we can just cross out this whole part. So half of 2 is 1, so 81 equals 1 times t squared, which is just 81 equals t squared, so you get 9. A cyclist accelerates from rest for 20 seconds at a rate of 0.40 meters per second squared. She then travels at a constant speed for 60 seconds. What is the top speed of the cyclist during the motion described is... Okay, so we have the initial velocity, which is 0. We have the acceleration, which is 0.4. We have the time, which is 20. And then we have another time, which is 60. So to find the top speed of the cyclist, we can do the formula, which does not have displacement. So V final equals V initial plus A acceleration times time. So after replacing, equals 0 plus 40, 0.440 times 20, you should get 8 meters per second. And for the net displacement of the cyclist, you're going to use the formula, which does not have the final velocity. So that's half of AT squared plus VIT. After replacing and everything, you get half of 0.40 times 20 squared plus... Okay, so we know the initial velocity is 0, so we can just cross everything after that out. So you get 80 meters, and that's for the first part of the displacement, because we're trying to find the net displacement. And now to find the second part of the, this part B, to find the other displacement, we can do displacement equals velocity times time, because we don't have an initial position. So the velocity which we got in this question was 8, and the time which we got for the second part is 60. So you get 480. So if you do 480 plus 80, you get 560 meters, which is the net displacement. A cyclist on his bike accelerates from rest and reaches the speed of 6 meters per second in 25 seconds. He then applies the brake and comes to rest after moving through 20 meters. So let's see what they give us. We have the initial velocity, which is 0, and we have our final velocity, which is 6. We have our time, which is 25. We have our final position, I think. We have our thingy, which is 20. And then we have our deceleration, which is 0. So we need to find the acceleration of the cyclist in the first leg. So the first leg is this. So let's see what we can do. Okay, so we need to use a formula without displacement. So we can use velocity final equals velocity initial plus acceleration times time. So our final velocity we said is 6. Our initial velocity we said is 0, especially in the first leg. Plus, I'm going to call it AH times 25 for the time. So you take 25 to the other side, and then you do 6 divided by 25 you get 0.24. Okay, so for part B, so this is the part of the question we're going to need. And we need something which does not have time in it, which is velocity final squared equals the initial velocity squared plus 2a delta x. So we get 0 squared equals 6 squared plus 2, and then I'm going to call acceleration h 20. So you can take the 6 to the other side. So you get negative 36 equals 40 h, and then you get negative 0.9. Make sure there's a negative because you are deaccelerating. A particle initially moving at 12 meters per second is deaccelerating at 3 meters per second squared. The displacement of the particle before coming to rest is... Okay, so we need to use the equation which does not have time, which is Vs squared equals Vi squared plus 2a delta x. So after replacing, you get 0 squared because it's deaccelerating, which means the final velocity is going to be 0, equals 12 squared plus 2 times negative 3, and I'm going to call displacement h, so times h. So you should get, after solving, you should get 24. The time it takes for the particle to come to rest is blank. So we need to find the time now. So we can use the formula with no displacement. So Vf equals Vr plus 80. So 0 equals 12 plus negative 3t. And you should get 4. An athlete starting from rest runs a 150 meters race on a straight track. He covers the first 18 meters with a constant acceleration of 3 seconds. He runs the remaining 132 meters with the same velocity. So the acceleration in the first 3 seconds is blank, and the velocity in the end of the first 3 seconds is blank. So the first leg is the acceleration of the athlete in the first 3 seconds. That's what we need to find first. So this is the first part of the equation which we're going to use. Like in the question, that's the part we're going to use. So we do the formula because we don't have a velocity final, so we use this formula. And after replacing, you just get your answer. Now we know that a velocity initial is 0. So we can just straight away cross that out, and I'm going to keep acceleration as h. After doing 1/2 times 9 and dividing it by 18, you should get 4. Oh guys, my bad, I forgot to add the half. The velocity of the athlete at the end of the first 3 seconds is blank meters per second. So let's write down the values we do have. Okay, so the initial velocity is 0 and our acceleration is 4. So and our time is 3. So we need to find the velocity final. So we can use the formula velocity final equals velocity initial plus acceleration times time. So the velocity final, so you do 0 plus 4 times 3 and you get 12. The total time the athlete takes to run the full 150 meters is blank seconds. So what we're going to do is we're going to use the formula Okay, the total time that the athlete takes to run the full 150 meters is blank seconds. So we can use the formula displacement equals velocity times time, but we need to get the time remaining. So we switch out the time and the displacement. So you get time equals the displacement over velocity. So this again stands for time remaining. So displacement over velocity, and then using the last part of the equation, it's going to be 132 over 12. And to do that, plus the time, which is 3, and you get 14 seconds, and that's the answer. Because it said he had about a third second. A jogger continuing to run at a speed of 2 meters per second along a straight path. This is a constant velocity because you're talking about speed and not velocity. A hammer is falling near the surface of a moon. This is acceleration. A kite moving in a straight line gaining 5 meters per second. So there's velocity, so 5 meters per second is velocity, so it's acceleration. And the box suddenly sliding down at an incline, it's constant velocity at 0.8 seconds. A truck accelerates uniformly from rest at 1 meters per second squared. What is the distance covered by the truck when it reaches a speed of 72 kilometers per hour? Choose the correct answer. So we need to first convert 72 kilometers per hour into meters per second. So you multiply it by 3.6 and you get 20 meters per second. And then we can use the formula of velocity initial equals our initial velocity is 0, our final velocity is 20, and our acceleration is 1. So we can use the formula delta x equals, we need to find delta x. So we can use the formula, find the velocity final equals velocity squared equals initial velocity squared plus 2 times 1 times h, and I'm going to call delta x h. The 1 is the acceleration, by the way. So 20 squared equals 0 squared plus 2h, and after solving you get, so 20 squared is equal to 400, and 400 divided by 2 is 200, so that's why h is equal to 200, so the displacement is equal to 200. To land safely, a jetliner decelerating uniformly at 7 meters per second needs a runway with a minimum length of 500 meters. What is the maximum touchdown speed of that jetliner? So we need to keep in mind that it's deaccelerating. So let's write down the values which we do have. So we have the final velocity, which is going to be 0. Deacceleration, which is 7. And the displacement, which is 500. So we can use the formula velocity final equals initial velocity squared over both of them to a delta x. So we need to find the initial velocity. So I'm gonna call this one h squared. So after replacing it, 0 squared equals h squared plus 2 times -7 because we're deaccelerating times 500. So you should get, after solving and stuff, you should get h2 equals 7,000, And when you square root that, you should get 83.7. She travels at a constant speed of 60 seconds. The top speed of the cyclist during the motion is blank meters per second. Okay, so to calculate the top speed, we're going to use the formula. Velocity final equals initial velocity plus AT. Replacing it, you get, I'm going to call this one H. So H equals 0 plus 0.40 times 20, and you get 8. And displacement of the cyclist during the entire motion is what? So we need to first calculate the displacement during the acceleration phase. So we can use the formula t squared. And after replacing, you get half of 0.40 times 0.20 squared, and we know that the initial velocity is 0, so we can just ignore that. Calculate the displacement. Now we need to calculate the displacement during the constant speed phase. So what we're going to do is displacement equals Vt. So we can do this equals 8 times 60, so you get 480. And then you do 480 plus 80 and you get 560. I feel like we did this question before. Okay.